Hello, and welcome to the 13th Topmotors webinar. Our topic today is standards for energy-efficient electric motor-driven systems. This webinar is organized by Energiezukunft Schweiz and Impact Energy, and it's also supported by the Swiss governmental program Energie Schweiz. My name is Bojana Gajic. I work at Energiezukunft Schweiz, and I will be your host today. Now, I would like to introduce our speaker for today's webinar. Conrad Brunner is an independent consultant based here in Switzerland in Zurich. He received master's degrees both from the Swiss Institute of Technology ETH in Zurich and from the University of Pennsylvania in Philadelphia. Conrad has been working for more than 40 years as a pioneer of energy efficiency in a broad field of international research, technology, and policy projects in the industrial, domestic, commercial, and transport sectors. In the last 15 years, he's been focusing on the efficient use of electricity in industry, namely energy-efficient electric motor-driven systems and standardization issues in this field. He has been engaged in the Swiss Topmotors program and in the international IEA Technology Collaboration Program for EMSA. Currently, Conrad is working as an international senior advisor, and he is engaged in IEC standards for electric motor-driven systems. Conrad, I'd like to thank you so much for joining us today. We're looking forward to your presentation about the impact of standardization and the development of electric motor system. The floor is now yours.
Hello everybody, thank you Bojana for the nice introduction. We are going to talk about the new global motor standards move the market, standards for energy efficient electric motor driven systems, but basically we talk about energy efficiency. That's the topic that has been on the focus of all our work for many, many years. On the picture you see below a motor exploded. On the left side you see the pulled out rotor with the shaft. In the middle you see the stator. On the right you see the cooling fan. That's sort of the most basic assembly of an electric motor. But the reality is like that. That means we don't deal with motors like individual standalone pieces. We talk with big electric motor-driven systems. In the picture there is a gas compression machine, and this machine has maybe a couple of pumps, couple of motors, couple of fans, couple of compressors, and the whole entire thing has to do the job it is designed for. That's our job. Now, the menu I'm going to show you is here. There are some slides that are headlined. First, I talk about electric motors, then about standards, then about the very important thing about the requirements. Then the second half will be about the system, the motor-driven system, and then I go to the future and draw some conclusions. Thank you for following me. We have, for the first time, this presentation in English, and we have from the registration more than 30 countries here. I salute the people from the US and from Canada and from Mexico who have to get up very early today, and I salute the people from China and Japan who have a nice afternoon together with us. Now, electric motor. That's the core of an electric motor-driven system. First, the importance of electric motor-driven systems. They drive pumps, fans, and compressors for air and compressors for cooling, but also transport systems, handling and process systems, and many other applications. On the right side, you see a recent survey made by the Lawrence Berkeley Laboratory for the US, and there have been many other surveys like that before. And what it shows that basically about 80% of the applications are the pumps, the fans, and the compressors. All the other things are also important, but mainly we have to talk about pumps, fans, and compressors. And altogether, that's the line on the bottom. Motors are responsible for 53% of global electricity demand. That means we are talking about a very important issue if it comes to energy efficiency. Now, let's talk standards. What are standards? Why do we need standards? First, there are two global standard makers. I've shown them on the top. It's the IEC on the left side and it's ISO on the right side. IEC is responsible for electric machines, from the television to the CD player to the motor, and ISO is responsible for the mechanical part of the machines, also for the CD player, which is a mechanical system, and for all other things like the pumps and the fans and the compressors. These two standard makers form the body internationally, globally, for what are standards. Standards are made by experts from industry. They are representatives. They come maybe also from academia, from non-governmental agencies, NGOs. The organization in the standard making procedure is like that. There are technical committees. For example, there's an IEC technical committee number 2 that deals with rotating machinery. That means motors and generators. In ISO, another example is the TC 117 that deals with fans. And then the procedure. How do we go about making standards? It's always somebody has to create a new work item. Somebody has to say it's very important now to make a standards for frequency converters. And then it goes to drafts. The committee, the technical committee or the working group makes drafts. Eventually goes to voting. The voting body are the national committees. In the case of the technical committee 2, it's about 30 countries who have a body who is voting on that. Then a final draft is produced and then it will be published. In this case, for example, the famous IEC 60034-2-1. That's a testing standard for motors. And when this procedure is finished, it goes again in a cycle of being revised. Now, how about the decision making? Who decides standards? Who has to follow standards? The standards are made when a 2/3 majority of the participating national committees agree. I mentioned there are about 30 countries. Each has a vote, and there is a sequence of vote in the draft phase and in the final phase. And if 2/3 of the countries agree, then a standard is published. The timelines usually takes 2 to 4 years to make a standard, and the revision is about after 5 years. What's the important part in standards for energy efficiency? There are 3 major questions you have to deal with. First is the definition of the scope. What product is in a standard, what is not treated in a standard? It seems like a trivial question, but it's a very important question. Then for all things that involve energy efficiency, we need a testing standard. How can you agree on a methodology for the determination of losses and efficiencies? And the third element is the efficiency classification. This has been launched since about 15 years, that the standard also have to include some kind of a scale which has to be agreed to measure and to talk about the energy performance. Now, I want to show why the accuracy and the repeatability of this testing is very important. I show you 4 circles. Number 1, there have been 10 measurements, and you see the little black dots on the circle. They're spread all over. That means we call that bad repeatability and bad accuracy. When you go to number 2, the dots are much closer together. We call that bad repeatability because they're not all in the center, but relatively good accuracy. When you go to point number 3 in the bottom, you show the 10 dots all very closely together. You have good repeatability, but actually they're off the point where you want to have them. Therefore, there's a bad accuracy. There's a systematic mistake in the testing. And then number 4, that's what we like to have. You have good repeatability and good accuracy. Why is this important? I show you what the efficiency classes and the efficiencies are for a relatively bad today, IE1 standard motor, IE2 high efficient motor, IE3 premium efficient motor, and IE4 super premium efficient motor. Now, when you look at these bars, they show the efficiency on the left and the vertical scale. You have their efficiency in percentage. I choose to show 3 types of motor. A very small one, 0.75 kilowatt, 1 horsepower. That's a light green. One middle size, very often used, 7.5 kilowatt. That's the middle green. And the middle, this large size, 75 kilowatt, is on the right side. Now, when I show you this, the tolerances. When you look at the tolerance, every motor test has a tolerance. And basically, between the very small ones and 100 kilowatt, 150 kilowatt, we talk about 15% tolerance of the losses. The red little squares I show on the top of the, in this case, 75 kilowatt motor, show what is the deviation that is allowed. And now when you look at it very closely, when you make the picture big again, you see that the tolerance of this one, IE2, the bottom line, is very close to the upper line of the IE1. That means the tolerances are relatively sensitive. And the bigger the motor, the higher the efficiency. If you go to IE3 or IE4 machines, these tolerance bands are very small. That means, going back to the left part of the graph, you really need a testing method that is agreed internationally, and that secures that you have good repeatability and good accuracy. That's the reason why testing is such a sophisticated procedure. I'll show you some example. That's a motor test laboratory that also had participated in a converter test, and here is all the equipment you see. It's a picture from the Cal Test laboratory in Australia. Now, when you look at the picture on the left side here, you see the converter on the test. On the bottom, you see the electronics. That's a flux voltmeter, and that's a power analyzer. And then in the middle, the blue part, you see the IE2 motor for loading the converter. And then on the right side, green, you see the that's a tongue breaker, the dynamometer machine for loading the motor. You need that, you need that, you need that. These are the three elements you want to test, and you need a high level of electronic to make sure that you are as accurate as I said before. Now, when you look at motor standards today, motor testing standards, they're quite mature. There has been a long decision making over the last 20 years, and since about 10 years, we can say we have an internationally agreed method to test motors with very, very good accuracy and very good repeatability. In the case of the converter standards, we are just starting. The first converter standard was published 3 years ago, and it had a description of testing which proved to be not so watertight. Therefore, we launched a new research program. It's called a round robin for converter losses. In the first phase, the 2017 to 2018, 4 international labs participated. The Australian lab, the Danish lab, the Swiss lab, and the US lab. They tested 50 times with 9 different converters between 0.75 kilowatt and 11 kilowatt, relatively small units, the biggest like that, the smallest like that, and they tested them on 24 different motors. The target of this, the goal of this first phase was to secure the testing methodology. And now I think we can proceed to the second phase, where the issue is between the last year and the end of this year to test a number of products to cover the whole and the entire band of size between 0.12 kilowatt and up to 1,000 kilowatt. There are about 60 different converters to be tested. By the end of this year, we'll have the result. And these 2 round-robin elements, the phase 1 for the method and the phase 2 for the actual loss determination, will form the basis that we can revise the respective IEC standard. Now, what's the business with this full load and partial load? This is a diagram from our colleagues in Belgium, Kurt Stockman and his crew at the University of Ghent. And it shows on the vertical axis the variation of torque between 0 and the top is 150%. In the upper third is the red little mark is on the 100% torque a machine has. On the bottom line, horizontal line, you see the speed. In the middle, you see 100% rotating speed. On the right side, you see 200%. Now, normally all business with motors and converters and their respective driven systems deal with that square. And we have taught people for a long time you shouldn't oversize your machine, because in this upper third of the square, of the white square, you have a relatively good system efficiency. System efficiency is the combined efficiency of the converter on the motor. In this case of a 4 kilowatt motor, you are certainly above 75% and you reach about 80% at the top. But what the graph shows, when you test in a much larger band, you go up to 150% of the torque and you go up to 200% of the speed. You really try to use the power the machine has. You actually note that the maximum of efficiency is somewhere here. There is an efficiency peak island, 81%, that is around, I would say, 75% of the torque, and here about 80% of the speed, and it goes way to the right, and hits about 130% of the speed and about 50% of the torque. What does that mean? That means the nominal sizing of a motor and a frequency drive to this 100% torque and 100% speed is fine. But when you look at a machine, typically a fan or a compressor or a pump, you might want to go to a zone in this efficiency band that comes more closely to the actual operation. And this already touches on the problem. If the motor feels very well and he's well within his rated performance square, that doesn't mean that the pump and the fan or the compressor he drives is also at its optimum performance point. Now we talk about requirements. A requirement is when a national regulator, sometimes it's a state like California, or national means the USA, or a group of countries like the European Union, they decide in their jurisdiction, they issue energy efficiency requirements for products sold. Typically, they describe what technical documents you have to deliver when you bring a product to the market, what kind of testing standards you have to use. If there are labels, you remember the refrigerators, they have label ABC, or in China 1, 2, 3. And also they define a minimum efficiency requirement. Under that and that testing conditions, you have to reach for that type of motor 92% efficiency. That's what the regulators do. Usually there's a timeline underlying, there's a decision making and a publication date, and then after 1 or 2 years delay, there's an enforcement start, and then there is also an upgrading. Usually you have a first period with 2 years, you require this level, and then after 2 years you require a higher level. And in some cases, like in Europe and in China, there's a reach level, usually typically a third level, that you ask for the future, that people who design machines and use machines know what's going ahead, what's going in the future. And important for all these requirements, you need to have a revision date. People have to know when the whole paper is revised. Now, I quickly show you 3 types, 3 countries, 3 groups of countries. And I show you the minimum energy efficiency requirements for motors. On the left side, Europe. Europe has an eco-design directive. It has a motor regulation that has been well known since 2009. It's the number 640, also used in many Asian countries. And now it just issued a new one, 1781. It was published last year and starts to be enforced from 21. And it covers the whole range between small ones, 0.12 and 1,000 kilowatt. Switzerland, not part of the European Union, but in Europe, has an Energy Act, an efficiency ordinance, and is synchronized with the European directive. That means it covers the same size, it covers all the same types. And then you have the USA, they have a Code of Federal Regulations. There's a part 431 that defines the energy efficiency programs. And then there's a subpart B like Berlin, for the electric motors, that goes from 0.75 kilowatt, that's 1 horsepower, up to 150, and for certain types to 375 kilowatt, that means up to 500 horsepower. And it has a subpart X, it's really X, it's for the small motors, they go from 0.18 to 2.2 kilowatt. What does that show? Before I talked about standards, which are global, and now we talk about requirements, and they are national. Only states or countries can decide what is a minimum performance requirement within their boundary. They will use basically the standards as a guideline, but the actual thing is in the national legislation. Now I quickly show you a development between 2009 and 2023 in Europe. I always use the same 4-pole 50 Hertz motor, and I show the minimum requirements, how they have been in law. And the first slide shows the status of 2009. The IEC standard, that is the baseline for these 4 efficiency classes, has been published. The standard is called IEC 60034-30-1, published in 2014, but the predecessor was already published. And here we show 4 efficiency classes. The red one, the IE1, is the standard efficiency. The yellow one, IE2, is the high efficiency. And the green one, the IE3 is the premium efficiency. And also the IE4 is already determined now. It's called the super premium efficiency. These curves are shown on the horizontal axis in a logarithmic scale. On the left you have 0.1 kilowatt, and then steps 1, 10, 100 and 1000 kilowatt to the right side. And you see what everybody knows, that the efficiency of a small machine is much lower than the efficiency of a bigger machines. And you see also these four curves that have a wide spread on the small size converge more or less with a couple of few percentage points at the right side above 200 kilowatt. And now, status of 2009, the IEC standard was issued, but requirements, nothing. Now we go forward. 2015, Europe decided first time to introduce a minimum requirement, and you see now two black lines. The upper black line on IE3 level was required between 7.5 kilowatt up to 375 kilowatt, and there's a dotted black line below that was introduced at the same time that as an alternative to the IE3 you could use an IE2 motor, that means a little bit less efficient, if you use it together with a variable speed drive. Now we go to 2017. That was the second tier of the European requirement. It was expanded to go from 0.75 up to 7.5 kilowatt. That means the black arrow shows the expansion, but it was the same game with the black line on IE3 and the black dotted line on the IE2 plus the variable speed drive. And now we go to 2021. That's now the new regulation decided last year, going to be enforced by next year, the middle of next year. And now it has a very dramatic change. It goes down to the very small motors from 0.12 kilowatt up to 0.75 kilowatt. Not yet at IE3 level, but IE2, but still, this is a vast group of motors that are produced in millions, used in all kinds of appliances, in your washing machines and many other machines, also in industry. They're used by the millions. As I said, they're manufactured all over the world. They usually have this little size. And up to now, except from the US, no real standard was available. And now we have a basic in the IEC standard, and that will be applied in China, in the US, and Europe at the same time. When we go forward, there's also a next tier in this new requirement in Europe, and you see the bump in the range of 75 to 200 kilowatt for the first time in the whole world, and we are very proud that this happens in Europe for the first time globally. The minimum requirement will be the IE4, the super premium efficiency motor. That means when you look back at the first slide, 2009 to 2023, that's something like 14, 15 years, the train has been moving in the right direction. Energy efficiency has become a major issue all around the globe. Now the reality test. This is the slow progress we see on the actual market. That's a picture from Switzerland because we have market surveys there that look at the figures relatively in detail. And I show you the blue is 2016, the red is 2017, and the green is 2018. And I show the four categories. IE2 is the largest, and you can actually see that the three bars, even there's a little progress between the 2016 and 2017. How come? And then it's stable, 2019. That's not really a very good sign. And then to the right, the IE3, there you can see a progress, but I would consider that not a dramatic progress. And then on the right side, still voluntary, not mandatory, you see the IE4. There, you see they're still at a very, very low number. Interestingly enough, there are also IE1 motors sold, but every year a little bit less, because there are applications, the famous garage opener that runs for 20 seconds every morning and 20 seconds every evening. They don't need to have a high-performant, energy-efficient motor. They can have a very simple, very cheap motor that doesn't have a cooling on it, no ventilation, and that can handle the job. But when you do real things, that means you want to have continuous operation, you have to a high-quality motor, and that should be IE3. And the IE2 in Europe is still there because of this industry compromise from 2009 to also allow IE2 together with variable speed drives. The problem is we don't know whether the people who have sold an IE2 motor or bought an IE2 motor for their application actually did what was required. That means use the motor together with a variable speed drive. But altogether you can say progress, but slow progress in the distribution of high efficient motors in Switzerland. Now let's talk about the most important part, the motor system. That's a very generic drawing of an electric motor-driven system. From the left side you have an input of electricity from the mains, then you have the motor control, then you have the electric motor, which is the converter between electricity and mechanical power. Then you have the mechanical equipment, and then you have the driven application. On the right side, you have the flow of the motor that goes then into the use that you actually have designed it for. That's a very generic, very simple graph. Now we go to the more detailed graph, which you might want to show big. Yes, on the left side, we don't talk about the actual input into the mains, which is the electricity production and distribution, the transformers, the power factor correction, or the uninterruptible power supply. And on the right side, we don't talk about the output user system, the distribution network, the pipes and the ducts, if you have a storage system, or if you add heating and cooling for your airflow or for your water flow. Also, we don't treat at that point the bypass or throttles. But between these two endpoints, on the left side the red dot, on the right side the red dot, this is the efficiency. We define the efficiency as the output divided over the input. When you look at the 4 squares on top of the greenish square in the middle, you can see what I showed just as a simple box, motor control. This means a lot of other things. Here are the switch gear, the control gear. Here is the converter, the variable frequency converter. There's the input-output filter, and maybe there's a cooling system necessary for the controller. Then in the motor, you have an AC motor, alternate current, or DC, direct current. You run it in 50 hertz in Europe and 2/3 of the world, or you run it in 60 hertz in the US, in Mexico, in Canada. You run it slowly at 8 poles, or average at 4 poles, or very fast at 2 poles. You have an external fan or not. You use a special cooling. You have a greasing pump. That means what is called an electric motor can be also a relatively complex system. I remind you of the second slide I showed at the very beginning. And then the mechanical equipment can be a gear, a belt and pulley, can be a brake and clutch. If you don't have any of that, you're well off and you're more efficient. But for many applications, it's still typically to run the motor for a fan over a belt and a pulley, even if that's an extra machine and extra cost and extra losses. And on the right side, on the driven application, we have pumps, but pumps can be single or multi-stage. You have fans. Fans have a filter. You have a compressor that can be also a single or a dual stage, has an air dryer, has a cooling system, has eventually a heat use, and you have all the transport and handling system. With this, I want to show you an electric motor-driven system is 4 squares. That's sort of the generic approach, but when you look a little bit at the detail, you see it's a much more complex installation that you have that consumes, as I said in the beginning, 53% of global electricity. Now, the system. What is the system? What does the system mean? What are the advantages of an electric motor-driven system? The system means you're not just looking at one component. You look at the cooperation in planning, assembly, testing, and operation of these 4 boxes. And the system integration has very big advantages. Most of the time, a composed integrated system is lighter, smaller, cheaper. It has a higher reliability. It has less waste heat. That means it's more energy efficient. It has a lower peak load. It has a lower electricity consumption in kilowatt hours and lower in cost. And it has improved controls when you start and stop it, when you run it at peak load or a part load, and over the whole hours of operation. The system is a very advantageous idea about how to run a machine, but it has these 4 squares, and that means it's a higher complexity. I want to show you this like that. When you look at the motor standards, the basic of the motor standards is just the motor. It has a testing standard and an efficiency classification. Then on the second line, you see a motor fed by a converter, by a variable frequency drive, has a separate testing standard and has a separate efficiency classification. Why is this needed? When you feed a motor from the grid with a 50 hertz and the perfect sinus, you get what you expect in efficiency. When you feed it from a converter that uses pulse width modulation, you don't give him a nice sinus, but you give him a staggered sine feed for the voltage and the current. That means the motor losses are a little bit higher. Then on the third line, you have actually the standard for testing the variable frequency drive itself, published in 2017. Here we can have a determination in calculation and measurement of VFD losses. And below on line 4, you have a motor and VFD together. Is also a standard coming up. It's what they call an extended product approach. And on the bottom line, my favorite, number 5, is when you look at the entire system. That's the new KaiSEMS program I want to mention shortly. There you include the 3 main elements. That means the variable frequency drive, the motor, and the application. This is necessary to achieve these advantages I just mentioned, but we agree it's a more complex way of looking at the world. These are again these different components that are part of a system standards. And now what happens? The left side, the power equipment, the controls, and the motor belong, so to say, to the IEC, the International Electrical Commission. They are the standard makers for the power equipment, for the controls, and for the motors. And when you look on the right side, that belongs to the ISO, the International Organization for Standardization. They make the standards for the coupling, the mechanical transmission, for the driven equipment, until the process components and mechanical controls. What does that mean? There are 2 standard makers, I mentioned them before, that deal with the entire electric motor-driven system. When you look at that, that's sort of like a family reunion. There are 3 bluish squares and 6 reddish squares. These are all the technical committees. 3 plus 6 makes 9. 9 technical committees deal with standardization, testing, efficiency classification, scope definition of the elements that are part of an electric motor-driven system. What does that mean? When you look at the numbers below the colored squares, you can see the date when they were founded. The oldest one, 1911, is the motor TC here. The most recent ones are from 64 or 65, the pumps, the fans, and the compressors. But still, I mean, 65, that's 55 years ago. These standard bodies, they control the knowledge of the industry in a specific field. And they are composed by experts that know exactly what is a motor, what is a variable frequency drive, what are gears, what are pumps, what are cooling compressors, etc. But so far, they have been working in relative separate worlds. That means they have been dealing with their component, and they have not spent very much time in exchanging information to their neighbors, which are really part of a fully functioning electric motor-driven system. This is what we want to change. This we want to work on. Therefore, we launched a project for a system standard. It's called the KaiSEMS project. The KaiSEMS project is part of IEC ACEE. That's the Advisory Committee on Energy Efficiency. That's a top committee below the Standard Management Board, and there is a task group 6 that controls or that guides this work. I'm the convener of this group. And the goal is the coordination and alignment of energy-efficient electric motor-driven systems. Seems very simple, coordination and alignment. It's a cooperation between IEC and ISO. That happened before, but it's new in this field. And the goal is to have new basic IEC and ISO standards for working together. Currently, the group has 60 members, 41 active and 19 passive. The first meeting was on 20 September 2019 in Tokyo, the launch, and the 4th meeting will be 20 November 2020, a little bit more than a year after the launch in Zurich. The future. Motors, as I showed on the very first slide, are not just stators and rotors and ventilation. Motors start to be intelligent systems. This is a line of 16 different robots. Each robot has a 6-axis defined geometric freedom. Each robot has at least 6 motors and converters. That means they try to form a movement that is comparable to when you have your arm and your hand and your fingers to touch something or to glue something or to weld something or to bring something into connection with something else. That's what a robot does. And he needs electric motors. And they have to be very precisely guided, that they can change their position and stay solid, put at a certain location. And they have to be highly efficient, otherwise they couldn't do that, they would overheat. Also, we need more and more network systems. A motor system is not a standalone anymore. You see that for electromobility, for cars, for trucks. They all have an internet address. They communicate with each other. In the case of traffic, the main goal is, of course, that they don't hit each other, but they also want to get information from their factory, whether their load has to be distributed in this and that sense. That means intelligent systems and network-oriented systems. Also in the different components, there is a lot of progress made every year, and you see water-cooled pumps, converter integrated pumps, and you see fans with outrunner, electrically commutated EC motors on the left with bionic blades from one manufacturer, on the right with profiled blade geometry. Interesting, they have the motor in the center and they have the fan outside, the blades. That means that's an outrunner. It's not, as I showed in the very beginning, where the rotor is in the center of the stator, but it's the other way around. In the center is the stator and the rotor is around, and that's actually what you need for fans very often. Also, there are now advanced technologies. Linear drives become more popular instead of the usual transportation bands. We need servo drives. Servo drives have been around for many, many years, but now in the robot technology, many other technology, they are very important because they can precisely make a movement and stay there for a given time. Also, there are advanced technologies coming from electromobility, from cars, in-wheel motors, also outrunners, water-cooled, air-cooled. Here, the question is to have a motor in the wheel of a car, of an electric car. That has to go through some different kind of qualifications. It not only has to have a high efficiency, but it has to change speed from 0 to 10,000 rotations per minute, and it has to be efficient. Otherwise, it would heat and it couldn't be so small. Therefore, the efficiency is key, and the cooling of these very intensely composed motors is very important. Now we come to the end. What happens now in the market is new applications for electric motor-driven systems appear. We used to start thinking about a refrigerator that has a compressor, or we used to talk about the fan that has a motor and some blades, and we used about the pump that has an impeller and the motor. But now the applications explode. We have electric cars, electric trucks, electric buses, even electric airplanes, like the famous solar impulse on the right. And funny enough, on the streets of Zurich, you see all these little things that people transport. They're actually highly efficient. They have a 100 or 200 watt motor. They can even climb. They have a battery, very small. Therefore, it's fantastic what happens right now in the mobility sector. And that influences, again, what happens in the industry sector. If you put it together on one little square, motor systems get smaller. Otherwise, you couldn't do that. They get lighter. They're getting more efficient. They stay cooler. Because they use less material, many of them are cheaper. They can accelerate. They can go to very high speeds, 10,000 RPM, 20,000 RPM when you have a racing car. They can brake actively. That means they use the energy that has been invested by accelerating for the braking. And they can be fed from batteries, plus they charge it, minus they get the power from the battery. That means the development in the last 10 years has been gigantic. And there is pretty good idea that also industrial applications for electric motor-driven systems and household applications and commercial building applications, like in the HVAC, will profit from that development. Conclusions. Well, progress is driven by technology. You use new materials, you use silicon carbide for variable frequency drive. You use amorphous steel for a better motor. Progress is also driven by competition, like a Japanese manufacturer wants to be smarter than a German manufacturer. It's also driven by ecology because many industries understand that what they do is in a larger context. They don't just want to use wasteful material that cannot be reused. And also, I want to emphasize this, progress is driven by governments with minimum requirements. In the case of Europe, in the case of the USA, these two governments have, and Australia also, have introduced minimum performance standards very early, and they really have driven the market. They have pushed the progress higher up, and they have thrown bad products out of the market. Second, internationally coordinated standards make it easier for national governments to establish minimum requirements for efficient products. If they are nationally coordinated standards that exist in China, that exist in India, that exist in the USA, that's fine. But if they are internationally coordinated, then it makes it much easier because most of these products are internationally traded. You don't want to have a German motor being shipped to Brazil and it has to be retested and reclassified because there other rules apply. Thirdly, IEC, the electric standard makers, and ISO, the mechanical standard makers, their standard committees need to interact much more closely. That they can deal with energy efficiency in electric motor-driven systems in a timely fashion. This is a reason we launched the Kaizems project, and I think it's going to be a successful venture for the next couple of years. And fourthly, intelligent electric motor-driven systems linked by network, like I tried to explain, from manufacturers, the network from a manufacturer to a consumer. New technologies and new applications stimulate innovation in systems. The motor development story is not finished yet. I would say it starts. And finally, the person who operates a machine and is responsible for its programming of this high-tech equipment is most likely the most important element to have a sufficient and high-efficient electric motor-driven system. That means, given all the high-tech, the people who operate it are very crucial. Thank you very much. These are my contact informations. On the right side, I show also the cover of the Topmotors Motor Market in Switzerland, Motor Market Report in Switzerland 2019. It's going to be published in the next few days. It has been an annual exercise supported by the Swiss government, and from that we know much more in detail what kind of motors, pumps and fans are actually put on the market and whether they comply with the requirements or not. That's it for my, thank you very much for your attention.
Okay, thank you very much, Conrad, for this very interesting presentation. Now, dear participants, it's your turn to ask questions. You can submit them using the chat function as explained in the technical part in the beginning of the webinar. All right, so let's start this Q&A session off with a question we received during the presentation. Question 1. What are operating points for testing the efficiency of a motor, a converter, a pump, and a fan not aligned? I repeat, why are the operating points for testing the efficiency of a motor, a converter, a pump, and a fan not aligned?
I got the question. It's a very crucial question. When we talk about electric motor-driven system, the coordination between all the major elements have to be well organized. And one of the elements for the coordination is to test the efficiency. And to test the efficiency, the motor manufacturer, the VFD manufacturer, and the pump manufacturer have to agree on a certain point that their load, their torque, and their speed, or if in the case of a pump, it's their head and their flow are tested. They have to be coordinated. Now, what happens if they're not coordinated? If they're not coordinated, you buy the most high-efficient motor, you buy an okay converter, because it's not so clear how they interact, and you buy a pump, but by totally different criteria. You cannot decide which type of pump will actually put your system on the right operating points. Now comes an important point. Motors are usually tested and converters the same at around their nominal or rated power, which is this, I showed it in this diagram, this is the contour curves with the white dotted line, it's 100% torque and 100% speed. But a pump or a fan, they're usually not operating there, they're operating at their best operating point, which might be 80% of the speed or 120% of the speed, and might be 60% of the flow or 80% of the flow. Therefore, the motor people have to start testing and having interpolation methods that they can deliver their efficiency values to the pumps requirements and to the fans requirements and to the compressors requirements. That's actually the task we started with Kaisems. And there's a lot of discussion how these points should be selected. It used to be very complicated to test a motor or a fan at several testing points. But now, in the age of electronic and digitalization, many of these systems can go through a testing robot to a machine that can cover a matrix with maybe 100 points, or you test 10 crucial points, and then you have an interpolation method, a tool, you can use your Excel tool, and then you find your actually necessary best operating point for your application. So there's a complication in this question, but there is a solution. We work in this direction, that we have coordinated operating points for testing the efficiency for all types of applications.
Thank you very much, Conrad. Moving on to the next question we received. When the European Union decides on motor maps, is this compulsory also in Italy and in Spain?
Yeah, that's a very interesting question. It used to be in earlier decisions of the European Union that was at times a 15-country union, then became a 28-country union. Currently, I think it's something like a 70-country union. There's one member, I forgot its name, I forgot who it is, that wants to leave, and I think there are some discussions how to leave. And in earlier decisions, the European Union decided on the directive, and then the individual countries had to adopt that direction into their national body of law. Now, with the minimum energy performance standards have been launched under the European umbrella of the Eco-Design Directive, and that includes the motors, the circulators, the water pumps, and the fans. Will continue to go to the compressors and to the elevators and to other applications. They have all gone through the same procedure. That means there's a lengthy way from technical studies and decision making at the level of the European Commission, with the respective Directorate General for Energy being responsible, and finally the European Parliament to decide on the regulation. But then immediately it is compulsory for all the 27 or 28 members. And that has sped up the implementation of these requirements in Europe very fast. I think basically we have the same situation in the US, that the central government decides and then all states have to adopt. In many cases, it was a little bit the other way around in the US, that some progressive countries like California would have more stringent requirements first, and then they pushed on the central government to adopt it also for the other countries. But it's a crucial element. This is crucial for large countries like in India, like in China, like in USA, or like in the European Union, that you have for one region, one national, in case of Europe, it's international group requirement that has to be adopted in every single one of them. And I think we are on the right track now with that.
Thank you, Conrad, again. Question number 3. What role do you think digitalization plays in evaluating the efficiency of a system, and how can standardization contribute?
Well, digitalization is sort of the hype that's going on. Digitalization has a big impact on how machines are designed. You design a prototype not by casting iron, but by a computer program. You used to have a first prototype, and then you measured its efficiency and checked whether it would fit with what you have designed it for. Today, also the simulation of the product can actually say something pretty close to the reality, how the efficiency will be. When you have the final product and it's in your catalog, you produce it and you deliver it, you also have something which is called a digital twin. That means at home, every machine, if it's a pump or a fan or a motor or a converter, has a digital program at the factory base that can go through all the operational stages, all the torque and speed and head and flow and whatever you have to have. And then you can quasi from home, see whether a machine that's delivered to 10,000 kilometers apart, how it operates, and whether the digital twin performs the same as the actual machine on the ground. This is very important when you have a failure, when you have delivered a machine, it doesn't operate perfectly, or it even operates in a different way as you have anticipated. That means not in every case you can go there easily when you're on an oil drilling platform out in the sea. It's very good to know that over the internet you can check in your digital twin whether your machines run properly or not. When you look at the efficiency I mentioned before the test was sort of a unique adventure which involved a lot of machinery. I showed you this picture, and it involved a lot of people, very precise measurements. You also almost have to be in a clean laboratory with controlled temperature and no dust in the air, no electromagnetic disturbance, etc. Today you can set up the same kind of lab, but then run it through a digitalized program. You can make a motor test within, I would say, 2-3 hours, and it goes to 100 points. Goes to every point and measures, waits for a couple seconds, moves to the next point, measures for a couple seconds, goes to the next, and at the end you have a protocol, a digital protocol, where you have for all the 100 points the respective values you want to have. Standardization plays a role. Standardization plays a role because factories have always resisted to doing too much testing work. Testing is for them a nuisance. We always had the point that if you want to manufacture superior products, you have to have your own testing. You have to make sure that the products have a high efficiency to begin with, and that you have low deviations in quality, that the products are really to the point. You have very small tolerances. When you have a new model, it's called an alternative determination of losses. It's used in the USA, the ADEM system. You can relieve part of the burden of the testing by requiring that you test, for instance, for the motor over the whole range, you only test 5 motors at 5 given points between 0.1 kilowatt and 1,000 kilowatt. And then you have a simulation program that determines or interpolates all the points in between. Therefore, with this, standardization can contribute, and digitalization is certainly a very important point. But just one thing, in one of the motor summits, we had a guy coming from a company that sells lubricants. And he was laughing at all our high-tech discussions on even higher materials being used in a rotating machine and so on. And he said at the end, if it's not well lubricated, it doesn't work. Therefore, you can have digitalization, you can have high-tech materials, you can have super digitalized controls, you can have remote controls, everything. But at the end of the day, it has to be well lubricated. That means it's still a mechanical machine.
Okay, thank you very much for these explanations. A further question we just received states, how long do you think it will take to issue efficiency standards for mechanical equipment? And how about ruling out worm gearboxes in favor of bevel or bevel helical?
For mechanical equipment, how long do you think it will take to issue efficiency standards? They exist for many. They exist for the pumps, the fans, the compressors. And worm gearboxes, that's another part of the questions. The first one, I would say, how long do you think? They are there. They will be improved. Everybody in the TC world, in the ISO world, in the pump section, 115, in the fan section, 117, in the air compressor systems, 118, the cooling compressor systems, 86. They are working on making these efficiency standards for mechanical equipment better and better and more precise, and to have what they don't have yet, have efficiency classification systems. Now, second part of the question, worm gearboxes. There are no standards. There are standards, but not standards for efficiency of gears. Within the world of gears, there are many different kinds. Gears work like that, like in a car gearbox. Gears that work like that, on 90-degree angle. And then there are gears work like that. That's what they call a worm gear. Worm gear is typically the one with the highest losses. They even become hot. It's an old-fashioned way of changing the force, the rotation you have in one axis to another axis, right? And the worm gear is something that was used. I'm not sure that they're going to work very much in this specific TC. It's an ISO TC, I think it's number 61 or something, or number 60, whether they're working on efficiencies and tests for worm gears. I think they're still struggling to get an efficiency test for all kinds of gears. And my hope was always, once the testing for all kinds of gears is established, and once what was anticipated also in the European Union, that the efficiency of a gear and also of a transmission, that means pulley and belt, would be included in the minimum requirement, then certain inefficient elements would be thrown out of the market. And worm gears are maybe one of the first to be thrown out.
Perfect, thank you so much. Question number 5. We just got a new machine with EFF1 on the technical shield, a completely new machine with new motors. But I thought EFF1 is not allowed since many years ago, for many years, and it should have therefore have the IE notifications. Is EFF1 on technical data shields still allowed?
Well, you find a lot of anachronisms in the motor world, and as everybody knows, on a rating plate, you can put almost any information you want. EFF1 or F1 was a European voluntary agreement between the European Motor Manufacturer Association, CEMEP, and the European Union. It was a EF1, EF2, EF3 things. EF1 is more or less equivalent of the new IE2. The system was launched in the 90s and it was abandoned, officially abandoned, once the IE2 IE code, IE1, IE2, IE3, IE4 classification came. And I would say when you want to sell a motor in Europe, it has to follow European requirements. That means it has to have an IE code classification printed. If it doesn't have it, it's not performing. It cannot have the CE mark. That means it's not compliant to the necessary requirements. You can refuse it. But on an old motor, you might find an F1, or in old catalogs, you still find EF1. Therefore, sorry, but it's not up to date.
Okay, thank you. We're coming to our final question now. You have correctly presented issues about the accuracy and repeatability of efficiency measurement. Unfortunately, the IEC standards do not define numerical targets for the extended uncertainty to be considered to validate the acceptability of the efficiency test. What is your point of view?
Well, they do not define numerical targets for the extended uncertainty to be considered to validate the acceptability of the efficiency test. Thank you, good question. Must be a high qualified expert to ask these things. First of all, the testing standard in IEC for motors 60034-2-1, I think it was, last edition was published 2014. It has a very important element. It gives about 6 different testing methods, and one is the preferred method. To determine a preferred method already limits the deviations you have when different people test on different points. Second, it has a tolerance. And thirdly, what's very important, it has on the last page, I helped to make it, a table where you put in all your test results. And you have to test the motor above 100% of speed, I think up to 125. And you have to give the values. That means the values provided by a manufacturer in the technical documentations show pretty much what the motor, how the motor has performed on the test. And if a guy like the person who asked this very good question sees this result, he can immediately determine himself the uncertainty you have involved. In certain tests, there is a formalized uncertainty calculation. And of course, the idea of the uncertainty is that you minimize 2 things. You minimize tolerances coming from the production of a motor. If your your 50 kilowatt motor has a normal efficiency at the nominal point of 100% torque and 100% speed, it has a performance of, say, 95%, that's fine. But you want to have the 95% when you produce a motor on Monday, on Tuesday, on Wednesday, and Thursday, and Friday. And not to have the Monday motors always having only 1% less. That's the quality control of the manufacturer. The other thing is the quality of the measurement. When you measure a motor performance, you have some critical elements. You have to measure the electric input. It's usually relatively precise, but you can have harmonics in the domains, whatever, and you measure the mechanical output, and for that you need a torque meter and a speed meter. And usually the torque meter is the most sensitive element. And there are people who can handle that. Many university labs do that. The university labs do it usually with the most high efficient equipment, but then they have some students running a lab test and they ruin the accuracy of the torque meter, and it has to be recalibrated, which is a lengthy procedure. That means these two elements, the performance quality of the manufacturing and the quality of the instruments you use for the measurement and the operation of the instruments, have to be put together to have a clear uncertainty calculation for the whole thing. If you have a motor manufacturer at hand, you can provide this data, and I think there's sufficient information in the standard that you can do that every user of these data can actually work with that very clearly.
Okay, perfect. Thank you very much, Conrad, for answering all these very exciting and interesting questions. Seeing as our time is up, I would like to conclude the Q&A session and ask our speaker, Conrad, for a brief final statement.
Well, thank you for listening to my presentation. You can have it, you can download it, and you can ask more questions. You have my contact details. Thank you for having had this large group of energy efficiency experts on the webinar. Thank you also for this growing community that Topmotors and Motor Systems from the IEA Annex, from the 4E EMSA has launched. And I think we have a growing community of experts in the field, and that has shown in the quality of the products that were put on the market. Energy efficiency has been a major consideration for the standard makers and for the regulators. But as I said in my presentation, we are not yet there. It's still a very important issue. We are talking about the largest chunk of electricity being used. Our climate problems are far from being solved. We have to work on that. We have to continue. There should be a younger generation joining us, and I think we'll make much more progress in the future. Thank you for your attention.
Okay, perfect. Thank you so much again, Conrad, for this very interesting presentation. Before I would like to quickly mention and announce the upcoming Topmotors events. We will be hosting 2 webinars this year. They will both be in German. The next one will be on September 9th about energy efficiency issues in compressed air systems. And the second one on November 25th, new concepts for efficient hydraulic drives. You can find all the details and free registration on the website. Okay, and furthermore, we will be offering a 6-day continuing education course in industrial energy optimization, which is organized in cooperation with 3 different universities of applied sciences. The course provides hands-on lab experience and deep functioning and the use of electric motors, frequency, drives, and motor systems such as pumps, fans, compressors, and chillers, and it has a special focus on energy efficiency. The course would be held in and in German in Horv, Lucerne, and then also in German in Basel. However, this year, due to the coronavirus pandemic, unfortunately, the course is in French in Yverdon, and the course in Horv, Lucerne in German are postponed. The course in Basel will take place as planned. More details regarding the courses can be found on the Topmotors website. And of course, we are very much looking forward to seeing you at our traditional Motor Summit 2020 International Conference, which will be held on the 18th and 19th of November in Zurich. For further information, please have a look at our website, www.motorsummit.ch. Okay, so in conclusion, I would once again like to thank our speaker, Conrad Brunner, for his excellent presentation, and of course you, dear audience, for your attention and active participation. If you have any questions regarding today's topic, please do not hesitate to contact either us or Mr. Conrad directly. We'd like to wish you a very nice day, and we'd be happy to have you with us during the next webinar. Thank you so much, and goodbye.